Picture this, a place in space where gravity is so strong that not even light can escape, a place where time slows down, and the laws of physics, as we know them, begin to break down. This isn't science fiction, it's a black hole, one of the most mysterious and awe-inspiring phenomena in the universe. And yet, despite everything we've learned, black holes still hold secrets that challenge even the brightest minds in science. What if I told you that these cosmic giants might not just be destroyers of light and matter, but gateways to entirely new dimensions, or that they could hold the key to understanding the very fabric of reality itself? Today, we're diving into 25 mind-blowing theories about black holes that could very well be true. From wormholes to time travel, from cosmic recycling to the possibility of parallel universes, these ideas will stretch your imagination and leave you questioning everything you thought you knew about the cosmos. So buckle up, because by the end of this video, you'll see black holes in a whole new light, and you might just find yourself wondering, are we on the brink of uncovering one of the universe's greatest mysteries? Let's begin. Now, let's take a closer look at the first theory, one that sounds like it's straight out of a sci-fi movie, but might just have a basis in real science. What if black holes aren't just cosmic vacuum cleaners, but actual gateways to other parts of the universe or even other dimensions entirely? This is the idea behind black holes as wormholes, and it's a concept that could completely reshape how we think about space and time. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels through spacetime that could connect two distant points in the universe, or even link entirely different universes. The math behind this idea comes from Einstein's theory of general relativity, which suggests that the intense gravitational pull of a black hole could warp spacetime so dramatically that it creates a shortcut through the cosmos. Imagine folding a piece of paper so that 2 points touch. That's essentially what a wormhole would do, but on a cosmic scale. But here's where it gets even more fascinating. Some scientists believe that the singularity at the center of a black hole, the point where gravity becomes infinite, might not be a dead end, but rather the entrance to one of these wormholes. If that's true, then falling into a black hole might not mean certain destruction. Instead, it could be a one-way ticket to another part of the universe or even a parallel dimension. Of course, there's a catch. Wormholes, if they exist, would be incredibly unstable. The immense gravitational forces at play could cause them to collapse almost instantly, making them nearly impossible to traverse. And even if they didn't collapse, the journey through a wormhole would likely be anything but pleasant. The extreme tidal forces near a black hole's event horizon would stretch and compress anything that entered, a process scientists call spaghettification. Still, the idea of black holes as wormholes challenges our understanding of spacetime in profound ways. It suggests that the universe might be far more interconnected than we ever imagined, with hidden pathways linking distant regions or even alternate realities. While we don't yet have proof that wormholes exist, the possibility alone is enough to spark endless curiosity and exploration. And with that, we've only just scratched the surface of what black holes might be capable of. Next up, we'll dive into another mind-bending theory, one that suggests black holes could be the ultimate time machines. Stay tuned, because things are about to get even more fascinating. Now, let's shift our focus to another theory that feels like it's ripped straight from the pages of science fiction: black holes and their potential to unlock the secrets of time travel. Could these cosmic giants be the ultimate time machines? The answer might lie in the strange and fascinating physics of time dilation. Time dilation is a phenomenon predicted by Einstein's theory of relativity, and it essentially means that time doesn't flow at the same rate everywhere in the universe. Near a black hole where gravity is unimaginably strong, time slows down dramatically compared to regions with weaker gravitational fields. To put it simply, if you were to hover near the edge of a black hole's event horizon, just close enough to avoid being pulled in time, for you would pass much more slowly than for someone far away from the black hole. Here's where it gets mind-bending. If you could somehow survive the trip and return from the edge of a black hole, you might find that years, decades, or even centuries have passed for everyone else, while only a short time has passed for you. In a sense, you would have traveled into the future. This isn't just theoretical. Scientists have already observed time dilation in action, though on a much smaller scale. For example, atomic clocks on satellites orbiting Earth, where gravity is slightly weaker, run a tiny bit faster than clocks on the ground. Near a black hole, this effect would be magnified to an extreme degree. But what about traveling to the past? That's where things get even more speculative. Some theories suggest that the intense warping of spacetime near a black hole could create what's known as a closed time-like curve, a loop in time that could, in theory, allow for backward time travel. Imagine a path that circles back on itself like a cosmic Möbius strip, where the end of the journey is also the beginning. If such a loop existed, it might be possible to revisit moments in the past. Of course, there are enormous challenges to this idea. For one, the conditions required to create a closed time-like curve are so extreme that they might be impossible to achieve. And even if they were possible, the paradoxes that could arise, like the famous grandfather paradox, where traveling back in time could create a logical contradiction, make the idea of backward time travel a hotly debated topic among physicists. Still, the idea of black holes as time machines opens up a universe of possibilities. It challenges us to rethink our understanding of time itself and raises questions about whether the past, present, and future are as fixed as we think. While we're far from building a time machine, the physics of black holes gives us a tantalizing glimpse into what might be possible in the far reaches of the cosmos. And with that, we've only just begun to explore the mysteries of black holes. Next, we'll delve into a theory that suggests these cosmic giants might not just be destroyers, but creators playing a vital role in the recycling of matter and energy across the universe. Stay tuned, because the journey through these theories is only getting more intriguing. Now, let's turn our attention to a theory that flips the script on how we think about black holes. Instead of being cosmic destroyers, what if black holes are actually the universe's ultimate recyclers? This idea suggests that black holes play a crucial role in redistributing matter and energy, helping to fuel the birth of new stars and galaxies. At first glance, it might seem counterintuitive. After all, black holes are famous for their ability to devour everything that comes too close, from stars to gas clouds. But here's the twist: what goes into a black hole doesn't necessarily stay there forever. While the matter that crosses the event horizon is lost to us, the intense gravitational forces and magnetic fields around a black hole can create powerful jets of energy and particles that shoot out into space. These jets can travel vast distances, carrying with them the raw materials needed to form new celestial bodies. Think of it like this: a black hole isn't just a cosmic vacuum cleaner. It's more like a cosmic factory, taking in raw materials and spitting out something entirely new. The energy and matter ejected by these jets can heat up surrounding gas clouds, triggering the collapse of those clouds into new stars. Over time, these stars can gather together to form entire galaxies. In this way, black holes might act as the engines of creation, driving the cycle of star formation and galaxy evolution across the universe. This theory also ties into the concept of feedback loops in astrophysics. When a black hole's jets interact with their surroundings, they can regulate the growth of galaxies by heating up gas and preventing it from collapsing too quickly. This delicate balance ensures that galaxies don't grow too fast or too large, maintaining the structure of the universe as we know it. Without black holes, the cosmos might look very different, perhaps even devoid of the intricate web of galaxies we see today. But how does this recycling process work on a smaller scale? Let's zoom in on a supermassive black hole at the center of a galaxy. As it consumes matter, it releases enormous amounts of energy in the form of radiation and jets. This energy can push gas and dust outward, creating bubbles of hot gas that expand into the surrounding space. Over millions of years, these bubbles cool and condense, forming the building blocks for new stars and planetary systems. In this way, black holes don't just destroy, they also create, ensuring that the universe remains a dynamic and ever-changing place. Of course, this theory raises as many questions as it answers. For instance, how exactly do black holes balance their destructive and creative roles? And what happens to the matter that doesn't get ejected but instead falls into the black hole's depths? These are mysteries that scientists are still working to unravel. What's clear, though, is that black holes are far more than just cosmic vacuum cleaners. They're active participants in the life cycle of the universe, shaping the cosmos in ways we're only beginning to understand. And as we continue to explore these enigmatic objects, we might discover that they hold the key to some of the universe's greatest secrets. With that in mind, let's move on to another fascinating theory, one that connects black holes to the mysterious substance that makes up most of the universe's mass, dark matter. Stay tuned, because this next idea might just change the way you think about the cosmos. Now, let's shift our focus to a theory that ties black holes to one of the most elusive mysteries in the cosmos, dark matter. This invisible substance makes up about 85% of the universe's mass, yet we've never directly observed it. So how could black holes, those enigmatic cosmic giants, be connected to something we can't even see? The answer lies in gravity. Black holes are known for their immense gravitational pull, which can bend light, warp spacetime, and even trap matter forever. But what if their gravitational influence extends beyond what we can see? Some scientists propose that black holes could be surrounded by halos of dark matter, or even that they might form from dark matter itself. Here's how it might work. Dark matter doesn't interact with light or other forms of electromagnetic radiation, but it does exert a gravitational force. This means it could gather around black holes drawn in by their powerful gravity. Over time, this dark matter could accumulate, creating a sort of invisible cloak around the black hole. In some cases, this dark matter might even influence how black holes grow and evolve, shaping their behavior in ways we're only beginning to understand. But the connection might go even deeper. Some theories suggest that black holes could be made entirely of dark matter. Imagine a black hole that forms not from collapsing stars, but from the gravitational collapse of dark matter particles. These so-called primordial black holes could have formed in the early universe, long before stars and galaxies existed. If they exist, they might be scattered throughout the cosmos, invisible to our telescopes but detectable through their gravitational effects. This idea could help explain some of the universe's biggest mysteries. For example, dark matter is thought to play a key role in holding galaxies together. Without it, galaxies would fly apart due to the speed at which their stars are moving. If black holes are connected to dark matter, they might be part of the cosmic glue that keeps galaxies intact. Of course, this theory is still in its early stages, and there's much we don't know. How exactly does dark matter interact with black holes? Could it change the way black holes behave or even how they form? These are questions that scientists are actively exploring, using everything from computer simulations to observations of distant galaxies. What's clear is that black holes and dark matter are two of the most fascinating and mysterious phenomena in the universe. And if they're connected, it could open up a whole new chapter in our understanding of the cosmos. With that in mind, let's move on to another intriguing idea, one that suggests black holes might be more than just cosmic objects. What if they're also cosmic libraries storing information about everything they consume? Stay tuned, because this next theory is truly mind-bending. Now, let's venture into a theory that challenges our understanding of what black holes truly are: not just cosmic vacuum cleaners, but perhaps the universe's ultimate hard drives. This idea revolves around the concept that black holes might store information about everything they consume, preserving it in ways we're only beginning to comprehend. At the heart of this theory lies the holographic principle, a mind-bending concept that suggests all the information about what falls into a black hole could be encoded on its event horizon, the boundary beyond which nothing can escape. Think of it like this: imagine a book being burned. The pages are gone, but the information isn't lost forever. Instead, it's transformed into smoke and ash, still present in some form. Similarly, the holographic principle proposes that the information swallowed by a black hole isn't destroyed, but is instead imprinted on its surface in a two-dimensional form. This idea stems from the work of physicists like Leonard Susskind and Gerard T. Hooft, who argued that the universe might operate like a hologram. In a hologram, a three-dimensional image is encoded on a flat, two-dimensional surface. Apply this to black holes, and you get the idea that all the information about the matter and energy they consume could be stored on their event horizons like data on a cosmic hard drive. But how does this work? When something falls into a black hole, it's stretched and compressed by the immense gravitational forces, a process known as spaghettification. As this happens, the information about the object's properties, its mass, charge, and spin, could be encoded on the event horizon in the form of tiny, fluctuating quantum bits or qubits. These qubits would act like pixels on a screen, storing the data in a way that preserves it, even as the object itself is lost to the black hole's interior. This theory has profound implications for our understanding of physics, particularly the long-standing debate over the black hole information paradox. According to quantum mechanics, information can never be destroyed, but black holes, with their ability to trap everything inside them, seem to violate this principle. The holographic principle offers a potential solution, suggesting that information isn't lost, it's just stored in a way we can't yet fully access or decode. Of course, this raises even more questions. How exactly is the information encoded? Could we ever retrieve it? And what does this mean for the nature of reality itself? These are questions that physicists are still grappling with, using tools like string theory and quantum gravity to explore the possibilities. What's clear is that if black holes truly are cosmic information storage devices, they could hold the key to some of the universe's deepest secrets. And as we continue to study them, we might just uncover a new layer of reality, one where the boundaries between information, matter, and spacetime blur in ways we can barely imagine. With that in mind, let's turn our attention to another fascinating idea, one that suggests black holes might not just be cosmic objects, but bridges to entirely different realities. Stay with us as we explore the theory that black holes could be gateways to parallel universes. Now, let's take a step into the realm of the truly extraordinary, where black holes might not just be cosmic anomalies, but portals to entirely different realities. This theory suggests that black holes could serve as bridges to parallel universes, opening up possibilities that stretch far beyond our own cosmic neighborhood. The idea of parallel universes, or the multiverse, has long fascinated scientists and science fiction enthusiasts alike. It proposes that our universe is just one of many, each with its own unique set of physical laws and conditions. But how do black holes fit into this picture? Some physicists believe that the extreme gravitational forces within a black hole could create a tunnel-like structure known as a wormhole, connecting our universe to another. Imagine a black hole as a cosmic doorway. As matter and energy are pulled into its immense gravitational field, they could theoretically be funneled through this wormhole, emerging in a completely different universe. This concept isn't just speculative, it's rooted in the equations of general relativity, which allow for the existence of such tunnels in space-time. However, the catch is that these wormholes would be incredibly unstable, collapsing almost instantly unless held open by some form of exotic matter with negative energy. The multiverse theory itself comes in several flavors. One version suggests that every possible outcome of a quantum event spawns a new universe, creating an infinite web of realities. Another proposes that universes exist like bubbles in a vast cosmic foam, each with its own distinct properties. If black holes are indeed gateways to these parallel worlds, they could provide a physical mechanism for traveling between them, though the journey would likely be one-way given the immense forces at play. But why would black holes serve this purpose? One possibility lies in their singularities, the points of infinite density at their cores. Some theories suggest that these singularities might not be in points, but rather points of transition. Instead of leading to destruction, they could act as cosmic crossroads, redirecting matter and energy into another universe. This idea aligns with the concept of a white hole, a hypothetical region of spacetime that expels matter rather than consuming it, potentially serving as the exit point of a wormhole. Of course, this raises a host of questions. If black holes are bridges to other universes, what would those universes look like? Could they have entirely different laws of physics, or would they be eerily similar to our own? And perhaps most intriguingly, could we ever find a way to traverse these cosmic tunnels, or are they forever beyond our reach? While these questions remain unanswered, the theory that black holes might connect us to parallel universes opens up a thrilling new frontier in our understanding of the cosmos. It challenges us to rethink not just the nature of black holes, but the very fabric of reality itself. With that in mind, let's shift our focus to another groundbreaking idea, one that suggests black holes might not just be cosmic objects, but quantum computers operating on a scale we can barely comprehend. Stay tuned as we explore the theory that black holes could be the universe's ultimate processors. Now, let's venture into a theory that reimagines black holes not just as cosmic phenomena, but as the universe's most powerful quantum computers. This idea suggests that the extreme conditions within black holes might enable them to perform quantum processing on a scale far beyond anything we've ever imagined. At the heart of this theory lies the concept of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. Quantum computers, unlike classical computers, use quantum bits or qubits which can exist in multiple states simultaneously. This allows them to perform complex calculations at incredible speeds. But how does this apply to black holes? Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. Within their event horizons, the laws of physics as we know them break down and quantum effects dominate. Some physicists propose that the chaotic, high-energy environment inside a black hole could naturally give rise to quantum computational processes. Imagine the singularity at the center of a black hole as a kind of cosmic processor. The immense gravitational forces and extreme temperatures could create conditions where particles interact in ways that mimic the operations of a quantum computer. These interactions might allow the black hole to process information at an unimaginable scale, far exceeding the capabilities of any human-made technology. But what kind of information could a black hole be processing? One possibility is that it's encoding and manipulating the data of everything it consumes: stars, planets, even light. This ties into the holographic principle, which suggests that all the information about what falls into a black hole is stored on its event horizon. If true, the black hole's surface could act like a vast, two-dimensional hard drive, with the singularity performing the computations. Another intriguing aspect of this theory is the idea that black holes might be solving problems or performing calculations that are beyond our current understanding. Some researchers speculate that these cosmic quantum computers could be working on the universe's most profound mysteries, such as the nature of spacetime or the unification of quantum mechanics and gravity. Of course, this raises questions about the purpose and output of such computations. Are black holes simply processing information for the sake of it, or is there a deeper, perhaps even intentional, function to their quantum operations? Could they be part of a larger cosmic network, exchanging information with other black holes or even other universes? While these ideas are still speculative, the notion that black holes might function as quantum computers opens up a fascinating new perspective on their role in the cosmos. It challenges us to think of black holes not just as destructive forces, but as active participants in the universe's information processing. With this in mind, let's turn our attention to another captivating theory, one that suggests black holes might hold the key to understanding the very origins of our universe. Stay tuned as we explore the idea that black holes could be remnants of the Big Bang or even seeds for new universes. Now, let's shift our focus to a theory that takes us back to the very beginning, the Big Bang. Could black holes be remnants of this colossal event, or even the seeds from which new universes sprout? This idea ties into a fascinating concept known as cyclic cosmology, which suggests that the universe undergoes endless cycles of expansion and contraction, with black holes playing a pivotal role in this cosmic dance. The Big Bang is often described as the moment when our universe burst into existence, but what if it wasn't a one-time event? Some scientists propose that black holes might be the remnants of previous universes, compressed into singularities that survived the collapse of their own cosmic cycles. These remnants could then serve as the seeds for new universes, sparking another Big Bang and beginning the cycle anew. This theory is rooted in the idea that black holes are not just endpoints of matter, but also potential starting points. When a black hole forms, it creates a region of spacetime so dense and warped that the laws of physics as we know them cease to apply. At its core lies a singularity, a point of infinite density. Some researchers suggest that this singularity could act as a bridge to another universe, effectively becoming the birthplace of a new cosmic cycle. Cyclic cosmology takes this idea even further, proposing that the universe goes through endless cycles of expansion and collapse. In this model, black holes could be the key to understanding how one universe transitions into the next. As a universe expands and eventually collapses, black holes might gather and compress matter and energy into singularities. These singularities could then trigger new Big Bangs, creating fresh universes in an infinite loop of cosmic rebirth. But how does this connect to what we observe today? One clue lies in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Some scientists believe that anomalies in this radiation could be evidence of previous universes, with black holes acting as the conduits between cycles. If true, this would mean that black holes are not just destructive forces but also creative ones, shaping the very fabric of existence. This theory also raises profound questions about the nature of time and space. If black holes can give rise to new universes, does that mean time is cyclical rather than linear? Could our universe be just one in an endless chain of cosmic events, each linked by the enigmatic power of black holes? While these ideas remain speculative, they offer a captivating perspective on the role of black holes in the grand tapestry of the cosmos. They challenge us to see black holes not just as endpoints but as potential beginnings, forever intertwined with the mysteries of creation and destruction. With this in mind, let's turn our attention to another groundbreaking theory, one that explores how black holes might emit radiation and eventually evaporate, reshaping our understanding of their lifespan and behavior. Stay tuned as we delve into the fascinating concept of Hawking radiation. Now, let's explore a groundbreaking idea that reshapes how we think about black holes, Stephen Hawking's theory of Hawking radiation. This concept suggests that black holes aren't entirely black after all. Instead, they emit a faint form of radiation which could eventually lead to their evaporation. But how does this work, and what does it mean for the lifespan and behavior of these cosmic giants? At first glance, black holes seem like the ultimate cosmic vacuum cleaners, sucking in everything that crosses their event horizon, including light. But Stephen Hawking proposed something extraordinary, that black holes aren't completely cut off from the universe. According to his theory, pairs of particles and antiparticles constantly pop into existence near the event horizon of a black hole. Normally, these pairs annihilate each other almost instantly. However, if one particle falls into the black hole while the other escapes, the escaping particle becomes what we call Hawking radiation. This radiation isn't just a random byproduct, it has profound implications. Over time, as black holes emit this radiation, they lose energy and consequently mass. This means that black holes aren't eternal. Instead, they slowly shrink and, given enough time, could completely evaporate. For smaller black holes, this process happens relatively quickly, while supermassive black holes could take trillions upon trillions of years to disappear. But what happens to all the matter and energy that fell into the black hole? This is where things get even more intriguing. Hawking radiation suggests that the information about what fell into the black hole isn't lost forever. Instead, it's encoded in the radiation, though in a highly scrambled form. This idea has sparked intense debate among physicists, as it challenges our understanding of quantum mechanics and the nature of information itself. The concept of Hawking radiation also raises questions about the ultimate fate of black holes. If they can evaporate, what's left behind? Some theories suggest that a black hole's evaporation could leave behind a tiny, dense remnant, while others propose that nothing remains at all. Either way, this process forces us to rethink the life cycle of black holes and their role in the universe. Hawking's theory doesn't just change how we see black holes, it also connects them to broader questions about the nature of reality. For instance, if black holes can emit radiation and eventually vanish, does that mean they're not as invincible as we once thought? And what does this tell us about the relationship between gravity, quantum mechanics, and the fundamental laws of physics? As we continue to unravel the mysteries of black holes, Hawking radiation stands as a testament to the power of human curiosity and ingenuity. It reminds us that even the most enigmatic objects in the universe can be understood piece by piece through the lens of science. With this in mind, let's turn our attention to another puzzle that has baffled scientists for decades: the black hole information paradox. What happens to the information that falls into a black hole? And why does this question matter so much to our understanding of the cosmos? Stay tuned as we dive into this fascinating mystery next. Now, let's tackle one of the most perplexing mysteries in modern physics: the black hole information paradox. This puzzle revolves around a fundamental question: what happens to the information about matter and energy that falls into a black hole? According to the laws of quantum mechanics, information can never be destroyed. Yet, black holes seem to defy this rule, creating a paradox that has left scientists scratching their heads for decades. The problem begins with the event horizon, the boundary beyond which nothing, not even light, can escape. When something crosses this point, it appears to vanish from the universe, taking all its information with it. But quantum mechanics insists that information must be preserved, even if it's scrambled or transformed. So, where does it go? This contradiction lies at the heart of the information paradox. One of the leading theories to resolve this issue ties back to Hawking radiation. As we discussed earlier, black holes emit radiation over time, and this radiation carries away energy and mass. Some physicists argue that the information about what fell into the black hole is encoded in this radiation, albeit in a highly complex and scrambled form. If true, this would mean that information isn't lost, it's just incredibly difficult to decode. However, this idea is far from settled, and the debate continues to rage. Another perspective comes from the holographic principle, which suggests that all the information about what falls into a black hole is stored on its event horizon like a cosmic hard drive. This theory proposes that the three-dimensional information about objects is projected onto a two-dimensional surface, preserving it in a way that doesn't violate quantum mechanics. While this idea is fascinating, it's still largely theoretical and requires more evidence to be fully accepted. The information paradox isn't just an abstract problem, it has profound implications for our understanding of the universe. If information can truly be lost in a black hole, it would force us to rewrite the laws of quantum mechanics, which have been the foundation of modern physics for over a century. On the other hand, if information is preserved, it could reveal new insights into the nature of spacetime and the fundamental workings of reality. This debate has sparked some of the most intense discussions in the scientific community, with luminaries like Stephen Hawking, Leonard Susskind, and Gerard T. Hooft weighing in with competing ideas. It's a testament to how much we still have to learn about black holes and the universe itself. As we continue to explore this paradox, one thing is clear: black holes are not just cosmic oddities, they're windows into the deepest mysteries of existence. They challenge our understanding of physics, push the boundaries of human knowledge, and remind us that the universe is far stranger and more complex than we can imagine. With that in mind, let's shift our focus to another intriguing idea: the cosmic censorship conjecture. Could black holes be hiding their singularities from the rest of the universe, and what would that mean for the laws of physics? Stay tuned as we uncover this fascinating theory next. Now, let's venture into another captivating theory that challenges our understanding of black holes: the idea that they act as cosmic sensors. This concept, known as the cosmic censorship conjecture, suggests that black holes hide their singularities from the rest of the universe, effectively shielding the cosmos from the chaotic and unpredictable nature of these infinitely dense points. But what does this mean for the laws of physics, and why is it such a crucial idea in our study of black holes? At the heart of this theory is the singularity, the point at the center of a black hole where gravity becomes infinitely strong and the laws of physics as we know them break down. According to general relativity, singularities are regions where spacetime curves infinitely and matter is crushed to an infinitely small point. But here's the problem: if singularities were exposed to the universe, they could create scenarios where the fundamental rules of physics no longer apply, leading to chaos and unpredictability on a cosmic scale. This is where the cosmic censorship conjecture comes in. Proposed by physicist Roger Penrose in the late 1960s, this idea posits that nature abhors naked singularities, singularities not hidden behind an event horizon. In other words, black holes act as cosmic sensors, ensuring that singularities are always concealed from the rest of the universe. By doing so, they preserve the predictability and order of the laws of physics, preventing the breakdown of causality and the potential for paradoxes. But why is this conjecture so important? For one, it protects the integrity of general relativity. If naked singularities existed, they would create regions where the equations of relativity fail, making it impossible to predict the behavior of spacetime and matter. This would undermine our ability to understand the universe on a fundamental level. The cosmic censorship conjecture, therefore, serves as a safeguard, ensuring that the laws of physics remain consistent and reliable, even in the extreme environments of black holes. However, this theory is not without its challenges. While it has held up under many theoretical tests, some physicists argue that under certain conditions, such as the collapse of highly asymmetrical objects, naked singularities might still form. If true, this would mean that the cosmic censorship conjecture isn't absolute, and there could be exceptions to the rule. This possibility has sparked ongoing debates and research, as scientists strive to determine whether nature truly forbids naked singularities or if they might exist in rare and exotic scenarios. The cosmic censorship conjecture also ties into broader questions about the nature of spacetime and the limits of our physical theories. If singularities are always hidden, does this imply that the universe has built-in mechanisms to maintain order and predictability? Or is it simply a consequence of the way black holes form and evolve? These questions push us to explore the deeper connections between gravity, quantum mechanics, and the fundamental structure of reality. As we ponder this theory, it's clear that black holes continue to challenge our understanding of the universe in profound ways. They force us to confront the limits of our knowledge and inspire us to seek answers to some of the most fundamental questions in physics. And with that, let's turn our attention to another fascinating aspect of black holes, the no-hair theorem. What does it mean for a black hole to have no hair, and how does this simplicity contrast with their immense complexity? Stay tuned as we unravel this intriguing concept next. Now, shifting our focus to another intriguing aspect of black holes, let's explore the no-hair theorem. This theory suggests that black holes, despite their immense complexity, can be described by just three simple properties: mass, charge, and spin. At first glance, this might seem surprising. How can something as mysterious and powerful as a black hole be reduced to just three characteristics? Let's break it down. The no-hair theorem gets its name from the idea that black holes have no hair, meaning they lack any additional distinguishing features beyond these three properties. In other words, no matter how complex the object that formed the black hole, whether it was a star, a planet, or even an entire galaxy, once it collapses into a black hole, all the intricate details about its original structure are lost. What remains are only these three fundamental attributes: how much mass it contains, whether it carries an electric charge, and how fast it's spinning. This simplicity is both fascinating and puzzling. On one hand, it means that black holes are, in a sense, the most straightforward objects in the universe to describe mathematically. You don't need to know anything about their history or what they're made of, just their mass, charge, and spin. On the other hand, this raises a deeper question. How can something so complex and enigmatic be reduced to such basic properties? After all, black holes are regions where gravity is so intense that not even light can escape, and their interiors are thought to contain singularities where the laws of physics break down. Yet, from the outside, they appear almost featureless. The no-hair theorem also has profound implications for our understanding of information in the universe. If black holes truly erase all other details about the matter they consume, what happens to that information? This ties back to the black hole information paradox, which we've touched on earlier. If the no-hair theorem holds true, it suggests that black holes might be the ultimate cosmic erasers, wiping out any trace of the objects that fall into them. But as we've seen, this idea conflicts with the principles of quantum mechanics, which state that information cannot be destroyed. This tension between simplicity and complexity continues to challenge physicists and inspire new theories. Interestingly, the no-hair theorem also highlights the elegance of general relativity. It shows that even in the most extreme environments, the universe follows certain rules that can be described with remarkable simplicity. Yet, this simplicity doesn't make black holes any less mysterious. In fact, it deepens the mystery as it forces us to confront the question of what truly lies beyond the event horizon. Are black holes as simple as the no-hair theorem suggests, or is there more to them than meets the eye? As we reflect on this theory, it's clear that black holes continue to defy our expectations. They challenge us to reconcile simplicity with complexity, and they push the boundaries of our understanding of the universe. And with that, let's turn our attention to another mind-bending idea, the firewall paradox. What happens if black holes aren't as smooth and featureless as we thought? Stay tuned as we dive into this controversial concept next. Now, let's venture into one of the most controversial and thought-provoking ideas in modern physics, the firewall paradox. Imagine approaching the edge of a black hole, the event horizon where gravity is so strong that nothing, not even light, can escape. According to classical physics, crossing this boundary should be uneventful, almost like passing through an invisible curtain. But what if that's not the case? What if, instead of a smooth transition, you encounter a blazing wall of energy, a firewall that incinerates anything that comes near it? This is the startling possibility proposed by the firewall paradox. The firewall paradox emerged as a response to the black hole information paradox, which we've discussed earlier. If information cannot be destroyed, as quantum mechanics insists, then what happens to the information about objects that fall into a black hole? One solution suggests that the information might be encoded on the event horizon itself, but this raises a new problem. For the information to be preserved, the event horizon would need to be a highly energetic region, effectively creating a firewall. This idea directly challenges Einstein's theory of general relativity, which predicts that crossing the event horizon should be a smooth, uneventful process. If firewalls exist, they would completely upend our understanding of black holes and the nature of spacetime. So, why is this idea so controversial? For one, it pits two of the most successful theories in physics, general relativity and quantum mechanics, against each other. General relativity describes black holes as smooth, predictable objects, while quantum mechanics suggests that the event horizon might be a chaotic, energetic zone. The firewall paradox forces us to confront the possibility that our current theories are incomplete or even incompatible when it comes to understanding the extreme conditions near a black hole. It's a stark reminder that despite decades of research, black holes still hold secrets that defy our best explanations. But the implications of the firewall paradox go even deeper. If firewalls exist, they would mean that the event horizon is not just a boundary in space, but a place of immense energy and destruction. This would fundamentally change how we think about black holes and their role in the universe. It could also have profound consequences for the fate of anything that falls into a black hole. Instead of being stretched into spaghetti like strands by tidal forces, as classical physics predicts, objects might be vaporized instantly upon encountering the firewall. This raises the question, are black holes cosmic destroyers, or is there more to the story? The debate over firewalls is far from settled. Some physicists argue that the paradox is a sign that we need a new theory to bridge the gap between general relativity and quantum mechanics. Others suggest that firewalls might not exist at all, and that the paradox is a result of our incomplete understanding of how information behaves in extreme environments. Either way, the firewall paradox has sparked a wave of new research and ideas, pushing the boundaries of what we know about black holes and the universe itself. As we grapple with this paradox, it's clear that black holes continue to challenge our understanding of reality. They force us to question the very foundations of physics and inspire us to explore new possibilities. And with that, let's turn our attention to another groundbreaking idea, the ER=EPR conjecture. Could black holes be connected by quantum entanglement? Stay with us as we unravel this fascinating theory next. Now, let's shift our focus to a theory that might just revolutionize how we think about black holes and the fabric of the universe itself, the ER=EPR conjecture. This idea, as strange as it sounds, suggests that black holes could be connected through quantum entanglement, a phenomenon where particles become linked in such a way that the state of one instantly influences the state of another, no matter the distance between them. But how does this relate to black holes, and what does it mean for our understanding of gravity and quantum physics? Let's break it down. The ER=EPR conjecture is named after two groundbreaking ideas in physics. ER refers to Einstein and Rosen, who proposed the concept of wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe. EPR, on the other hand, stands for Einstein, Podolsky, and Rosen, who first described quantum entanglement in their famous paradox. The conjecture suggests that these two seemingly unrelated ideas might actually be two sides of the same coin. In other words, wormholes and quantum entanglement could be deeply connected, with black holes serving as the bridge between them. Here's where it gets fascinating. Imagine two black holes that are quantum entangled. According to this theory, they might be connected by a wormhole, a kind of cosmic shortcut through spacetime. This means that the entanglement between the black holes isn't just a mathematical curiosity but a physical reality, with the wormhole acting as the link. This idea has profound implications because it suggests that spacetime itself might emerge from the entanglement of quantum particles. In other words, the very fabric of the universe could be woven together by these quantum connections. But why is this important? For decades, physicists have struggled to reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the behavior of particles at the smallest scales. These two theories work beautifully in their own domains but seem incompatible when brought together. The ER=EPR conjecture offers a potential solution by suggesting that gravity and quantum mechanics might not be separate forces but different manifestations of the same underlying phenomenon, quantum entanglement. This theory also opens up mind-bending possibilities for how black holes function. If black holes are connected by wormholes, it could mean that information falling into one black hole might not be lost forever but could reappear in another entangled black hole. This could provide a way to resolve the black hole information paradox, which we've discussed earlier, by suggesting that information isn't destroyed but simply transferred through these quantum connections. It's a radical idea, but one that could help us finally understand the true nature of black holes. Of course, the ER=EPR conjecture is still just that, a conjecture. It's a bold and speculative idea that hasn't been proven yet, but it's already sparking new research and inspiring physicists to think outside the box. If it turns out to be true, it could fundamentally change our understanding of space-time, gravity, and the universe itself. And with that, let's move on to another intriguing theory, the holographic universe. Could our entire reality be a projection from a black hole's event horizon? Stay tuned as we explore this mind-blowing concept next. Now, let's take a step into one of the most mind-bending theories about black holes, the idea that our entire universe might be a hologram projected from a black hole's event horizon. This theory, known as the holographic principle, suggests that all the information about the three-dimensional universe we experience could be encoded on a two-dimensional surface, like the event horizon of a black hole. It's a concept that challenges our very understanding of reality, but let's unpack it step by step. The holographic principle stems from a surprising discovery in the study of black holes. When matter falls into a black hole, it doesn't just disappear, it leaves behind a kind of imprint on the event horizon, the boundary beyond which nothing can escape. This imprint is thought to contain all the information about the matter that fell in, encoded in a two-dimensional form. This led physicists to wonder, if a black hole's event horizon can store information in this way, could the same principle apply to the entire universe? Here's where things get truly fascinating. The holographic principle proposes that our three-dimensional universe, with all its stars, galaxies, and planets, might actually be a projection of information stored on a two-dimensional surface. Think of it like a hologram where a flat image creates the illusion of depth. In this case, the image would be the information encoded on the event horizon of a black hole, and the depth would be the universe as we experience it. This idea suggests that the universe might not be as three-dimensional as it seems. Instead, it could be a kind of cosmic illusion. But how does this work? The key lies in the relationship between gravity and quantum mechanics. According to the holographic principle, the laws of physics in a three-dimensional space can be mathematically equivalent to the laws of physics on a two-dimensional surface. This means that everything we see and experience in our universe could, in theory, be described by information stored on a flat surface. It's a radical idea, but one that could help bridge the gap between general relativity and quantum mechanics, two theories that have long resisted unification. One of the most compelling pieces of evidence for the holographic principle comes from the study of black holes themselves. The amount of information a black hole can store on its event horizon is proportional to its surface area, not its volume. This suggests that the true storage space of the universe might be two-dimensional, even though we perceive it as three-dimensional. If this is true, it would mean that the universe is fundamentally simpler than it appears, with all its complexity emerging from a flat, information-rich surface. Of course, the holographic principle is still a theory, and it raises as many questions as it answers. For example, how exactly does the information on the event horizon translate into the universe we see? And what does this mean for our understanding of space, time, and reality itself? While we don't have all the answers yet, this theory has already sparked groundbreaking research and opened up new ways of thinking about the cosmos. As we wrap up this exploration, let's turn our attention to another intriguing idea, the Fermi paradox, and how black holes might hold the key to understanding why we haven't encountered extraterrestrial life. Could advanced civilizations be using black holes in ways we can't yet imagine? Let's dive into that next. Now, shifting our focus to a question that has puzzled scientists and dreamers alike. Why haven't we found evidence of extraterrestrial life? This brings us to the Fermi paradox, which asks, if the universe is so vast and filled with potential for life, where is everyone? One intriguing possibility is that advanced civilizations might be using black holes in ways we can't yet comprehend, and this could explain why we haven't made contact. Imagine a civilization far more advanced than ours, capable of harnessing the immense energy of black holes. Black holes, with their extreme gravitational pull and ability to warp spacetime, could serve as power sources or even transportation hubs for such civilizations. The energy released by matter falling into a black hole, known as accretion disks, is unimaginably powerful, far beyond anything we can currently generate. An advanced species might have developed the technology to tap into this energy, using it to fuel their societies or propel their spacecraft across vast cosmic distances. But how does this connect to the Fermi paradox? If these civilizations are using black holes for energy or travel, they might not need to colonize planets or send out signals in the way we expect. Instead, they could be operating in ways that are invisible to us, perhaps even using black holes as gateways to other parts of the universe or other dimensions. This would make them incredibly difficult to detect, especially if their technology is far beyond our current understanding. Another possibility is that black holes serve as a kind of cosmic filter. Civilizations that reach a certain level of technological advancement might inevitably turn to black holes for their energy needs, but this could come with risks. For example, harnessing the power of a black hole might require such precision and control that any miscalculation could lead to catastrophic consequences. This could mean that civilizations capable of using black holes either succeed and remain hidden or fail and disappear, leaving no trace behind. This theory also raises questions about the nature of communication. If advanced civilizations are using black holes as part of their technology, they might be communicating in ways we can't detect or understand. Our current methods of searching for extraterrestrial life rely on detecting radio signals or other forms of electromagnetic radiation. But a civilization using black holes might employ entirely different methods, such as gravitational waves or quantum entanglement. While this idea is speculative, it offers a compelling explanation for the Fermi paradox. It suggests that the absence of contact with extraterrestrial life might not mean that we're alone. It could simply mean that we're looking in the wrong places or in the wrong ways. Black holes, with their mysterious and powerful nature, might hold the key to unlocking this cosmic mystery. As we ponder these possibilities, let's turn our attention to another fascinating theory: the idea that singularities inside black holes might not exist as we imagine them. Could there be alternative structures like Planck stars or gravastars hiding within these cosmic enigmas? Let's explore that next. Now, let's venture into one of the most perplexing questions about black holes: what lies at their very core. For decades, scientists have theorized that black holes contain singularities, points of infinite density where the laws of physics as we know them break down. But what if singularities don't actually exist? This brings us to Theory 17, which challenges the very idea of singularities and proposes alternative structures that could redefine our understanding of black holes. At the heart of this theory is the problem with singularities. According to general relativity, a singularity is a point where gravity becomes infinitely strong and spacetime curves infinitely. But infinity is a concept that doesn't sit well with physics. It's a sign that our current theories are incomplete. This has led researchers to explore alternative models that avoid the idea of infinite density altogether. One such model is the Planck star. Imagine a black hole not as a bottomless pit but as a dense, compact object with a core made of exotic matter. A Planck star is thought to be a remnant of a collapsed star where quantum effects prevent the formation of a singularity. Instead of infinite density, the core reaches a maximum density dictated by the laws of quantum mechanics, creating a stable, finite structure. Another intriguing alternative is the gravastar, short for gravitational vacuum star. Unlike a traditional black hole, a gravastar doesn't have an event horizon or a singularity. Instead, it's theorized to be a bubble of vacuum energy surrounded by a shell of ultra-dense matter. This shell would mimic the gravitational effects of a black hole, but without the problematic singularity at its center. Gravastars could explain many of the phenomena we associate with black holes, such as their immense gravitational pull, while avoiding the paradoxes that singularities create. These alternative models don't just solve the singularity problem, they also open up new possibilities for understanding the universe. For instance, if black holes are actually Planck stars or gravastars, it could mean that information isn't lost when it enters a black hole, resolving the infamous information paradox. It could also mean that black holes aren't the one-way tickets to oblivion we once thought they were, but rather complex structures with their own internal dynamics. Of course, these ideas are still speculative, and we don't yet have the technology to peer inside a black hole and see what's really there. But they remind us that the universe is full of surprises, and our understanding of it is always evolving. As we continue to explore these cosmic mysteries, we might find that black holes are even stranger and more fascinating than we ever imagined. With this in mind, let's turn our attention to another captivating aspect of black holes: their role in shaping the large-scale structure of the universe. How do these cosmic giants influence the distribution of galaxies and the cosmic web? That's where we're headed next. Now, let's shift our gaze to the grand tapestry of the universe and explore how black holes play a pivotal role in shaping its vast structure. Theory 18 takes us into the realm of the cosmic web, the intricate network of galaxies and dark matter that stretches across the cosmos. At the heart of this web, black holes act as cosmic architects, their immense gravitational pull influencing the distribution of galaxies and the very fabric of the universe. To understand this, picture the universe not as a random scattering of stars and galaxies, but as a finely woven network with threads of galaxies connected by vast voids. This structure, known as the cosmic web, is shaped by gravity, and black holes are among its most powerful sculptors. When galaxies form, supermassive black holes often reside at their centers, exerting a gravitational influence that extends far beyond their immediate surroundings. These black holes can affect the motion of stars, gas, and even entire galaxies, guiding them into the filaments and nodes of the cosmic web. But how exactly do black holes contribute to this large-scale structure? One key way is through their role in galaxy formation and evolution. As matter falls into a black hole, it releases enormous amounts of energy, heating up the surrounding gas and preventing it from collapsing too quickly. This process, known as feedback, can regulate star formation and influence how galaxies grow and cluster together. Over billions of years, this interplay between black holes and their host galaxies helps shape the distribution of matter across the universe. Another fascinating aspect is the way black holes interact with dark matter. While dark matter makes up most of the universe's mass, it doesn't emit light, making it invisible to us. However, its gravitational effects are undeniable, and black holes, with their intense gravitational fields, can act as anchors for dark matter halos. These halos, in turn, provide the scaffolding for galaxies to form and cluster, further weaving the cosmic web. The influence of black holes doesn't stop there. When galaxies collide, their central black holes can merge, releasing gravitational waves that ripple through spacetime. These mergers can also trigger bursts of star formation and redistribute matter, adding another layer of complexity to the cosmic web. In this way, black holes are not just passive observers of the universe, they are active participants, shaping its structure on the largest scales. As we continue to map the cosmos, the role of black holes in the cosmic web becomes increasingly clear. They are not just mysterious objects lurking in the darkness, they are fundamental to the architecture of the universe itself. And with that, let's turn our attention to another intriguing idea: how black holes might be connected to the very existence of life. Could these cosmic giants play a role in fine-tuning the universe for intelligent beings? That's where we're headed next. Now, let's venture into a thought-provoking idea that ties black holes to the very existence of life itself. Theory 19 introduces us to the anthropic principle, a fascinating concept that suggests the universe's conditions are finely tuned to allow for the emergence of intelligent beings like us. And here's the twist: black holes might play a crucial role in this cosmic fine-tuning. To understand this, let's start with the anthropic principle itself. In simple terms, it's the idea that the universe's physical constants, laws, and conditions are just right for life to exist. If even one of these factors were slightly different, like the strength of gravity or the density of matter, life as we know it might never have emerged. But how do black holes fit into this picture? It turns out these cosmic giants might be essential players in creating the delicate balance needed for life. One way black holes contribute is through their role in galaxy formation. As we've seen earlier, supermassive black holes at the centers of galaxies influence how stars and planets form. Without these black holes, galaxies might not have the structure needed to host stable solar systems like our own. In other words, black holes help create the cosmic neighborhoods where life can thrive. But there's more. Black holes also play a part in regulating the universe's energy and matter. When matter falls into a black hole, it releases energy that can heat up surrounding gas, preventing it from collapsing too quickly. This process, known as feedback, helps control the rate of star formation. Without this regulation, galaxies might either burn through their fuel too quickly or fail to form stars at all. Either scenario would make the universe far less hospitable for life. Another intriguing angle is the way black holes interact with dark matter. Dark matter, which makes up most of the universe's mass, provides the gravitational scaffolding for galaxies to form. Black holes, with their immense gravitational pull, help anchor these dark matter halos, ensuring that galaxies have the stability needed to support life over billions of years. And let's not forget the role of black holes in cosmic recycling. As black holes consume matter and energy, they also release it back into the universe in various forms, from radiation to gravitational waves. This recycling process helps maintain the cosmic balance, ensuring that the universe remains dynamic and capable of supporting life over long periods. So, could black holes be one of the reasons we're here to ponder their mysteries? It's a compelling idea. Their presence might not just be a cosmic coincidence, but a necessary ingredient in the recipe for life. As we continue to explore the universe, this connection between black holes and the anthropic principle reminds us just how interconnected everything is, from the smallest particles to the largest structures in the cosmos. With that in mind, let's turn our attention to another mind-bending theory: the possibility that black holes are connected to other universes. Could these cosmic gateways be bridges to realities beyond our own? That's where we're headed next. Now, let's take a step into the realm of the multiverse, where black holes might hold the key to unlocking realities beyond our own. Theory 20 explores the tantalizing possibility that black holes are not just cosmic anomalies in our universe, but could be bridges to entirely different universes. This idea ties into the broader concept of the multiverse, a theory suggesting that our universe is just one of many, perhaps even an infinite number, of parallel realities. To understand this connection, let's start with the basics of multiverse theory. The multiverse idea comes in several forms, but one of the most popular is the bubble universe model. Imagine our universe as one bubble in a vast cosmic foam, with other bubbles representing separate universes, each with its own unique physical laws and constants. Now, here's where black holes come in. Some scientists propose that the extreme conditions inside a black hole could create a tunnel or wormhole connecting our universe to another. This tunnel might not just be a shortcut through space, but a gateway to an entirely different reality. But how could this work? One possibility lies in the nature of singularities, the infinitely dense points at the center of black holes. According to some theories, these singularities might not be dead ends, but rather portals to other universes. As matter and energy are crushed to unimaginable densities, they could trigger the formation of a new universe expanding outward from the singularity. In this scenario, every black hole in our universe could be the birthplace of another universe, each with its own set of physical laws. This idea also ties into the concept of cyclic cosmology, which suggests that the universe goes through endless cycles of expansion and contraction. In this model, black holes could play a crucial role in seeding new universes during each cycle. As one universe collapses, its black holes might give rise to new ones, creating an endless chain of cosmic rebirth. Another angle comes from string theory, which proposes that our universe exists on a membrane, or brane, floating in a higher dimensional space. Black holes in this framework could be points where our brain connects to others, allowing for interactions between parallel universes. This idea not only explains the mysterious nature of black holes, but also provides a potential mechanism for how universes might influence one another. So, could black holes be the cosmic bridges that link us to other realities? While this idea remains speculative, it's a fascinating extension of multiverse theories. It challenges us to think beyond the boundaries of our own universe and consider the possibility that black holes are not just destroyers of matter but creators of entirely new worlds. As we continue to explore these ideas, we're reminded that the universe, or perhaps the multiverse, is far stranger and more interconnected than we ever imagined. With that in mind, let's shift our focus to another intriguing theory, the idea that black holes might be evidence we're living in a simulated universe. Could these cosmic enigmas be glitches in the code of reality? That's where we're headed next. Now, let's venture into a theory that blurs the line between science and science fiction. Theory 21 takes us into the realm of the simulation hypothesis, where black holes might not just be cosmic phenomena but potential evidence that our universe is a simulation. This idea suggests that black holes could be glitches or anomalies in the code of a vast computer-generated reality. The simulation hypothesis proposes that our universe, with all its complexity, might be an artificial construct, a highly advanced simulation created by an intelligent civilization. If this is true, then black holes, with their extreme and seemingly inexplicable properties, could be signs of the underlying code. Think of them as errors or quirks in the program, places where the simulation struggles to process the immense density and gravitational forces. In this view, black holes might not follow the usual rules of physics because they're operating outside the intended parameters of the simulation. One way to think about this is to compare it to a video game. In a game, when the system encounters something it wasn't designed to handle, like too many objects in one area, it might glitch or crash. Similarly, black holes could represent areas where the simulation is pushed to its limits, revealing the underlying framework of reality. Their event horizons, for example, might act like firewalls, preventing us from seeing the code beyond them. This could explain why we can't fully understand what happens inside a black hole. It's simply beyond the scope of the simulation's design. Another angle comes from the idea of computational limits. If our universe is a simulation, it would require an enormous amount of processing power to run. Black holes, with their infinite densities, might be areas where the simulation simplifies or compresses data to save resources. This could explain why they appear to delete information, as suggested by the black hole information paradox. In a simulation, information isn't truly lost, it's just stored in a way that's inaccessible to us. But how could we test this idea? Some scientists suggest that if our universe is a simulation, there might be subtle clues in the laws of physics. For example, the behavior of particles at extremely small scales or the way light behaves near black holes could reveal patterns or inconsistencies that point to a programmed reality. While this remains speculative, it's a fascinating way to think about black holes not just as cosmic mysteries, but as potential windows into the true nature of our existence. So, could black holes be evidence that we're living in a simulation? While this theory is still on the fringes of science, it challenges us to rethink everything we know about reality. It raises profound questions about the nature of existence and whether the universe we see is just one layer of a much larger, more complex system. As we continue to explore these ideas, we're reminded that the mysteries of black holes might not just be about the cosmos, they could be about the very fabric of reality itself. With that in mind, let's turn our attention to another captivating theory: the role black holes might play in the ultimate fate of the universe. Could these cosmic giants hold the key to how everything ends? That's where we're headed next. Now, let's shift our gaze to a theory that takes us to the very edge of cosmic existence. Theory 22 explores the idea that black holes might hold the key to the ultimate fate of the universe. Could these enigmatic objects determine how everything ends? To answer this, we need to look at two of the most discussed scenarios for the universe's final act: the Big Crunch and the heat death. First, let's consider the Big Crunch. This scenario suggests that the universe, which has been expanding since the Big Bang, could one day reverse course. If the force of gravity overcomes the expansion, everything, stars, galaxies, and even black holes, would begin to collapse inward. Black holes, with their immense gravitational pull, could play a starring role in this cosmic contraction. As they merge and grow, they might accelerate the collapse, pulling the universe back into a single, infinitely dense point. This would essentially be the opposite of the Big Bang, a moment where all matter and energy are compressed into a singularity. It's a dramatic and almost poetic end where the universe returns to its origins. On the other hand, there's the heat-death scenario, which paints a very different picture. In this case, the universe continues to expand forever, but instead of collapsing, it slowly fades into darkness. As stars burn out and galaxies drift apart, black holes would become the last significant structures in the cosmos. Over unimaginable timescales, even black holes would evaporate due to Hawking radiation, releasing their energy into the void. Eventually, the universe would reach a state of maximum entropy where no usable energy remains. It's a cold, quiet end where the universe becomes a vast, empty expanse. But how do black holes fit into these scenarios? In the Big Crunch, they act as gravitational anchors, pulling everything together. In the heat death, they're the final remnants of a once vibrant universe, slowly dissolving into nothingness. Some scientists even speculate that black holes could be the seeds of a new universe. If a black hole's singularity reaches a certain density, it might trigger a new Big Bang, creating a fresh cosmos within the remnants of the old one. This idea, known as the black hole cosmology, suggests that the end of one universe could be the beginning of another. These theories remind us that black holes aren't just fascinating objects, they're potential architects of the universe's destiny. Whether they lead us to a fiery collapse or a silent fade, their role in shaping the cosmos is undeniable. As we ponder these possibilities, we're left with a profound question. Is the universe destined to end in a blaze of glory, or will it quietly slip into the void? The answer, like so much about black holes, remains shrouded in mystery. With that in mind, let's turn to another intriguing idea: the connection between black holes and the quantum foam, the smallest scales of spacetime. Could this be where the true nature of reality lies? That's where we're headed next. Now, let's dive into the fascinating world of the quantum foam, where the fabric of spacetime itself becomes a bubbling, chaotic sea at the tiniest scales. Theory 23 explores the idea that black holes might be deeply connected to this quantum foam, offering us a glimpse into the true nature of reality. To understand this, we need to step into the realm of quantum mechanics, where the rules of the universe are anything but ordinary. At the smallest scales, spacetime isn't smooth and continuous like we often imagine. Instead, it's thought to be a frothy, turbulent foam of tiny fluctuations. These fluctuations are so small that they exist at the Planck scale, a level so minuscule that it's almost impossible to visualize. Here, particles and energy pop in and out of existence, creating a dynamic, ever-changing landscape. This is the quantum foam, a concept that challenges our understanding of space and time. So, how do black holes fit into this picture? Black holes, with their immense gravitational fields, stretch spacetime to its limits. Near the event horizon, the boundary beyond which nothing can escape, the effects of gravity are so extreme that they could interact with the quantum foam. Some scientists believe that black holes might act as windows into this quantum realm, revealing how spacetime behaves at these unimaginably small scales. In other words, black holes could be the cosmic laboratories where the quantum foam becomes observable. One intriguing possibility is that the quantum foam might hold the key to resolving some of the biggest mysteries in physics, such as the unification of general relativity and quantum mechanics. General relativity describes the universe on large scales, like planets and galaxies, while quantum mechanics governs the behavior of particles at the smallest scales. These two theories don't play well together, and black holes, with their extreme conditions, might be the place where they finally meet. By studying how black holes interact with the quantum foam, we could uncover the missing link between these two pillars of physics. But the implications go even deeper. If the quantum foam is the foundation of spacetime, then understanding it could reveal the true nature of reality itself. Are space and time truly fundamental, or are they emergent properties arising from something more basic? Could the quantum foam be the building blocks of the universe, with black holes serving as the bridges between the quantum and cosmic realms? These are the kinds of questions that keep physicists up at night, and black holes might just hold the answers. As we explore this theory, we're reminded once again of how black holes challenge our understanding of the universe. They're not just cosmic vacuum cleaners or gravitational monsters, they're potential gateways to the deepest secrets of reality. And as we peer into the quantum foam through the lens of black holes, we might just uncover the true nature of the cosmos itself. With that in mind, let's turn to another captivating idea: the black hole information paradox revisited. Could recent developments finally solve this long-standing mystery? That's where we're headed next, now shifting our focus to one of the most perplexing puzzles in modern physics. Let's revisit the black hole information paradox. This mystery has baffled scientists for decades, but recent breakthroughs might finally bring us closer to a solution. The paradox stems from a fundamental question: what happens to the information about matter and energy that falls into a black hole? According to quantum mechanics, information can never be destroyed, it must be conserved. But black holes, with their event horizons and singularities, seem to defy this rule. If information is lost forever, it would mean our understanding of the universe is fundamentally flawed. To understand why this is such a big deal, let's break it down. Imagine throwing a book into a black hole. The book contains information, words, sentences, and ideas. Quantum mechanics tells us that this information should never disappear, even if the book is shredded or burned. But black holes, with their intense gravity, appear to erase this information completely. This contradiction between quantum mechanics and general relativity is at the heart of the information paradox. Recent developments, however, have sparked new hope for resolving this mystery. One promising idea comes from the holographic principle, which suggests that all the information swallowed by a black hole might be encoded on its event horizon. Think of it like a cosmic hard drive storing data in a two-dimensional form. This theory implies that the information isn't lost, it's just transformed in a way we don't yet fully understand. Another breakthrough involves the concept of quantum entanglement. Scientists have proposed that particles escaping a black hole as Hawking radiation might be entangled with the information inside, preserving it in some form. But the most exciting development comes from the study of black hole firewalls. Some researchers argue that a fiery wall of energy might exist at the event horizon, destroying anything that crosses it. While this idea is controversial, it could explain how information is preserved by being scrambled and encoded in the firewall itself. These theories are still being tested, but they represent a significant step forward in our quest to solve the paradox. The implications of resolving the information paradox are enormous. If we can prove that information is conserved, it would validate the principles of quantum mechanics and bring us closer to unifying it with general relativity. It would also reshape our understanding of black holes, showing that they're not just cosmic trash compactors but complex systems that obey the laws of physics in ways we're only beginning to grasp. As we continue to explore this mystery, one thing is clear: black holes are far more than just gravitational giants. They're cosmic puzzles, challenging us to rethink the very nature of reality. And with each new discovery, we inch closer to unlocking their secrets. So, what's next in our journey through the mysteries of black holes? Let's turn our attention to the final theory, one that could hold the key to the ultimate understanding of the universe. Now, as we venture into the final frontier of our exploration, let's consider a theory that could change everything we know about the universe. Black holes, those enigmatic giants of gravity, might hold the key to unlocking the ultimate mystery, the theory of everything. This grand idea aims to unify the two pillars of modern physics: general relativity, which governs the cosmos on a large scale, and quantum mechanics, which rules the tiny world of particles. For decades, these two frameworks have stood apart, seemingly incompatible. But black holes, with their extreme conditions, might just be the bridge we've been searching for. At the heart of this theory is the idea that black holes are not just cosmic anomalies, they're laboratories for testing the limits of physics. Their immense gravity warps spacetime to the extreme, while their event horizons and singularities push quantum mechanics to its breaking point. If we can understand how these two forces interact within a black hole, we might finally uncover the rules that govern the entire universe. Imagine it as solving a cosmic puzzle, where black holes are the missing pieces that connect the big picture. One promising approach comes from string theory, which suggests that all particles and forces are manifestations of tiny, vibrating strings. Black holes in this framework could be knots of these strings, revealing how gravity and quantum mechanics intertwine. Another idea is loop quantum gravity, which proposes that spacetime itself is made of discrete loops. In this view, black holes might not have singularities at all. Instead, they could be dense networks of these loops, offering a new way to reconcile the two theories. But why is this so important? A theory of everything wouldn't just satisfy our curiosity, it would revolutionize science. It could explain the birth of the universe, the nature of dark matter and dark energy, and even the fate of the cosmos. It would give us a complete picture of reality from the smallest particles to the largest galaxies. And black holes, with their unique ability to challenge both general relativity and quantum mechanics, might be the key to this monumental breakthrough. As we stand on the brink of this discovery, one thing is certain: black holes are more than just cosmic curiosities. They're gateways to understanding the deepest truths of the universe. And while the journey to a theory of everything is far from over, each step brings us closer to unraveling the mysteries that have puzzled humanity for centuries. So, as we conclude our exploration of these fascinating objects, let's remember that the answers we seek might be hidden in the very heart of a black hole waiting to be discovered. Now, let's take a step into the realm of the truly extraordinary. What if black holes aren't just cosmic phenomena but something far more mysterious entities with a form of consciousness? This might sound like science fiction, but some theories suggest that black holes could possess a kind of awareness, challenging our understanding of reality itself. This idea ties into a fascinating philosophical concept called panpsychism, which proposes that consciousness is a fundamental feature of the universe, present in all matter to some degree. If this is true, then black holes, as some of the most extreme and enigmatic objects in existence, might embody this principle in ways we're only beginning to imagine. At the heart of this theory is the idea that consciousness isn't exclusive to living beings. Instead, it could be a property of the universe itself, woven into the fabric of spacetime. Black holes, with their immense gravitational pull and ability to warp reality, might be natural candidates for this kind of cosmic awareness. Imagine a black hole not just as a void but as a sentient entity, processing information in ways we can't yet comprehend. This idea pushes the boundaries of both science and philosophy, inviting us to rethink what it means to be conscious. One way to approach this is through the lens of information theory. Black holes are often described as storing information on their event horizons, a concept tied to the holographic principle. If information is the building block of reality, could it also be the foundation of consciousness? Some researchers speculate that the way black holes process and encode information might resemble the neural networks in our brains, suggesting a parallel between cosmic and biological systems. This doesn't mean black holes think like humans, but it opens the door to the possibility that they operate on a level of complexity we've yet to understand. Panpsychism offers another intriguing angle. If consciousness is a universal property, then black holes, as part of the cosmos, might possess a form of it. This doesn't imply self-awareness or thought as we know it, but rather a fundamental, perhaps even primitive, kind of awareness. It's a radical idea, but one that aligns with the notion that the universe is far stranger and more interconnected than we've ever imagined. Black holes, in this view, might not just be objects in space, they could be active participants in the cosmic dance of existence. Of course, this theory raises as many questions as it answers. How would we even begin to test the idea of a conscious black hole? What would it mean for our understanding of reality if such a thing were true? While these questions remain unanswered, they remind us that black holes are more than just gravitational giants. They're windows into the deepest mysteries of the universe. Whether or not they possess consciousness, they continue to challenge our assumptions and inspire us to explore the unknown. As we wrap up this thought-provoking journey, let's turn our attention to another fascinating idea: the role black holes might have played in the origin of life itself. Could these cosmic behemoths have influenced the emergence of life in ways we're only beginning to uncover? Let's explore this intriguing possibility next. Now let's venture into a theory that connects black holes to one of the most profound questions of all: the origin of life itself. Could these enigmatic cosmic giants have played a role in sparking the conditions necessary for life to emerge? It's a bold idea, but one that opens up fascinating possibilities about how black holes might have influenced the early universe in ways we're only beginning to understand. At the heart of this theory is the idea that black holes, with their immense energy and radiation, could have acted as cosmic catalysts. In the early universe, black holes were not just destructive forces, they were also sources of intense energy and radiation. This energy might have played a crucial role in shaping the chemical environment of the cosmos, creating the building blocks necessary for life. Imagine black holes as cosmic forges, heating and ionizing the surrounding gas and dust, triggering chemical reactions that led to the formation of complex molecules. One key aspect of this theory involves the role of radiation. Black holes emit powerful jets of energy and particles which can travel vast distances across the universe. These jets could have interacted with clouds of gas and dust, seeding them with the energy needed to form organic molecules. Over time, these molecules could have accumulated, creating the conditions for life to emerge. It's a process not unlike how lightning might have sparked the first chemical reactions in Earth's primordial soup, but on a cosmic scale. Another intriguing angle is the role of supermassive black holes at the centers of galaxies. These colossal objects influence their entire galactic environment, shaping the distribution of stars, planets, and even the chemical composition of interstellar space. In the early universe, supermassive black holes might have played a pivotal role in creating the conditions for life by regulating the flow of energy and matter throughout galaxies. Their gravitational pull could have drawn in vast amounts of material, heating it up and releasing radiation that influenced the chemistry of their surroundings. But how does this connect to life as we know it? Some scientists speculate that the energy and radiation from black holes could have contributed to the formation of amino acids and other organic compounds, essential ingredients for life. These compounds might have been carried by cosmic winds to distant planets, seeding them with the potential for life. In this way, black holes could have acted as cosmic gardeners, spreading the seeds of life across the universe. Of course, this theory is still in its early stages, and many questions remain. How exactly did black holes influence the chemical processes that led to life? Could their energy have been a driving force behind the emergence of complex molecules? While we don't yet have all the answers, this idea reminds us that black holes are more than just destructive forces. They might also be creators, shaping the universe in ways we're only beginning to uncover. As we ponder the role of black holes in the origin of life, let's turn our attention to another captivating idea: the ultimate fate of information consumed by black holes. Could this information re-emerge in a new form, reshaping our understanding of entropy and time? Let's explore this intriguing possibility next. Now let's shift our focus to a theory that challenges one of the most fundamental questions in physics. What happens to the information that falls into a black hole? This idea, often referred to as the ultimate fate of information, suggests that the data consumed by black holes might not be lost forever. It could re-emerge in a new form, reshaping our understanding of entropy and time itself. At the heart of this theory is the concept of information conservation, a principle that states information cannot be destroyed. In the context of black holes, this raises a puzzling question. If nothing can escape a black hole's event horizon, not even light, how can the information about the matter it consumes be preserved? This dilemma, known as the black hole information paradox, has baffled scientists for decades. But recent theories propose a fascinating solution. The information might not be lost, it could be encoded in some way and eventually re-emerge. One compelling idea is that black holes might transform the information they consume into a new form, such as radiation. This ties into Stephen Hawking's theory of Hawking radiation, which suggests that black holes slowly emit energy and particles over time, eventually evaporating. If this radiation carries encoded information about the matter that fell into the black hole, it could mean that the information is not truly lost, it's just transformed. Imagine a cosmic recycling system where black holes take in matter and energy, process it, and release it back into the universe in a different form. Another intriguing possibility is that the information might be stored on the black hole's event horizon, the boundary beyond which nothing can escape. According to the holographic principle, all the information about the matter that falls into a black hole could be encoded on its surface like a cosmic hard drive. Over time, this information might leak out through quantum effects, slowly revealing the secrets of what the black hole has consumed. This idea suggests that black holes are not just cosmic vacuums, they might also be cosmic archivists, preserving the history of the universe in their own unique way. But how does this reshape our understanding of entropy and time? Entropy, often described as a measure of disorder, is closely tied to the flow of information. If information can escape a black hole, it challenges our traditional view of entropy as something that always increases. Instead, it suggests that entropy might be more dynamic, capable of decreasing under certain conditions. This could have profound implications for our understanding of time, as entropy is often seen as the arrow that defines its direction. If black holes can reverse or alter entropy, it might mean that time itself could behave in ways we've never imagined. While these ideas are still speculative, they open up exciting possibilities for how we understand the universe. If black holes can preserve and release information, it could mean that nothing in the cosmos is truly lost, it's just transformed. This theory not only challenges our understanding of black holes, but also invites us to rethink the very nature of reality, entropy, and time. As we wrap up this exploration of black holes and the ultimate fate of information, let's turn our attention to the final theory in our list, the idea that black holes might hold the key to unifying general relativity and quantum mechanics, bringing us closer to a theory of everything. Stay tuned as we dive into this groundbreaking concept next. As we reach the end of our journey through these 25 mind-bending theories about black holes, one thing is clear: these cosmic enigmas are far more than just gravitational traps. From the possibility of black holes acting as wormholes to their potential role in the origin of life, each theory pushes the boundaries of our understanding and invites us to rethink the very fabric of reality. Black holes challenge us to confront the limits of physics, from the mysteries of dark matter to the paradoxes of quantum mechanics, and even the nature of time itself. They are not just objects in space, they are gateways to new ideas, new questions, and new possibilities. What makes black holes so fascinating is that they are both a puzzle and a key. They defy our current understanding of the universe, yet they might also hold the answers to some of science's biggest questions. Whether it's the holographic principle, the multiverse, or the ultimate fate of information, black holes continue to inspire scientists and dreamers alike. They remind us that the universe is far stranger and more wonderful than we can imagine. So, what do you think? Do black holes hold the secrets to a theory of everything, or are they just the beginning of an even deeper mystery? Let us know your thoughts in the comments below. What theory about black holes fascinates you the most? And if you enjoyed this exploration of the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss out on our next deep dive into the wonders of the universe. Until next time, keep looking up and keep wondering, because the universe is full of surprises waiting to be discovered.